Alright, in this video we'll be going through impedance and current in an RC circuit. In the last video we looked at the phase relationship between the current across the capacitor and the current across the resistor in an RC circuit. As a quick reminder, if we have our RC circuit where we have our AC power supply and we have our capacitor here and our resistor over here, the voltage across the resistor, which we can denote as VR, leads the voltage across the capacitor, which we can denote as VC. And as you can see, the voltage across the resistor leads the voltage across the capacitor by 90 degrees, okay? So again, in the last video, we looked at how in order to find the voltage of the supply, we can't just simply add up the voltages across our components like we can in a regular DC circuit. What we needed to do instead is we needed to do vector addition of the voltage across the resistor and the voltage across the capacitor. And so what we got is our voltage across our resistor, like so, and then the voltage across our capacitor coming down, and this resultant vector is our supply voltage, okay? So our supply voltage comes down, like so, in our phase diagram. And so therefore, the voltage across our supply squared is equal to the voltage across our resistor squared plus the voltage across our capacitor squared, okay? And so therefore the voltage across our supply is equal to square root voltage across our resistor squared plus the voltage across our capacitor squared, okay? So as we can see here, the voltage of our supply, the voltage across our resistor, and the voltage across our capacitor are all out of phase. However, for our current, the current is the same at all points in the circuit. So this statement is pretty important, so I'm going to highlight it like so. Okay, now it's also important to note that the current is still oscillating, okay? So our current isn't constant, it's just the same at every point. So our current is also oscillating, like so. So we have our I and then our negative I. So it's also oscillating, okay? However, if we take the current at a particular time, call it time t, and let's say it's this value right here, okay? Therefore, the current at this particular time is going to be the same across every point in the circuit, okay? And this is obviously due to the fact that we have a series circuit for our RC circuit, okay? And so what that means is that we can use Ohm's law and reimagine our phasor diagram, okay? So let's say our resistor has a resistance of R and our capacitor has a capacitance of C. We can therefore say, because current is the same at all points throughout the circuit, we can say that the voltage across our resistor is equal to the current times the resistance, okay? And obviously this is an application of Ohm's law, okay? And we can do a very similar thing for our capacitor. If we apply Ohm's law to this, we can say that the voltage across our capacitor is equal to the current times the reactance of our capacitor. And for our supply, it's our current multiplied by this new quantity, which we can call Z or Z. And this Z is our impedance, okay? So this is our Z value. And remember, this manipulation of our phasor diagram is all made possible because the current at each point in the circuit is the same, okay? So now, what is impedance? Okay, so we can bring this over here, okay? So our impedance is the total of the combined resistances and reactance in a circuit, okay? Now this makes sense because both our resistance and our reactance is both measured in ohms, okay? And so therefore we can just add them up and we get a new quantity which we can call impedance. And because our resistance and our reactance are both measured in ohms, therefore our impedance is also going to be measured in ohms, okay? And so therefore if we apply Ohm's law across our power supply, we get Vs is equal to the current multiplied by the impedance of the circuit. So because of this, because the current is the same at all points throughout the circuit, we can simplify this phasor diagram to get a relationship between the reactances and the resistance and the impedance of the circuit, okay? So if we take this phasor diagram and move it down here, okay? Because the current is the same at all points throughout the circuit, we can get rid of the current, divide by the current, okay? And what we get is a phasor diagram of the resistances and the reactance and the impedance. And so therefore, from here, we can make our right angle triangle like we did for our voltages, and we get our resistance coming to the right, our reactance coming downwards, and therefore our total impedance is our resultant vector, like so. And therefore, we can say that our total impedance squared is equal to our resistance squared plus our reactance squared of our capacitor, okay? And so therefore, our impedance is equal to square root the resistance squared plus the reactance of the capacitor squared, okay? Okay, so we've dug it into the ground, that the current is the same at all points throughout the circuit. However, we still know that the current is fluctuating. And so where is it in our phase diagram? We know it's the same at all points, but is it in phase with any of our components? And in fact, it is. It is in phase with the voltage across the resistor. Okay, so we can draw in our current phasor like so. So our current is in phase with the voltage across the resistor. Okay, and so that is a very important point. So many of your NCEA questions will require you to have this knowledge. So current is in phase with the resistor voltage. Okay, so again, this is another very important point. And so the reason behind this is because the resistor is not affected by the frequency of the supply. So the resistor is not affected. So this is unlike our capacitor, because remember, the reactance of the capacitor is affected by the frequency, because we remember our reactance of our capacitor is equal to 1 all over the angular frequency multiplied by the capacitor. And so this right here, the angular frequency, shows that our reactance is affected by the frequency of our supply, okay? So we can see this not through any crazy derivations or anything, just through intuition, okay? If we have a phasor diagram over here, okay, like so, and we split it up into quarters, and let's call this part positive max, okay? So if the phasor is pointing this way, we know it's positive max, and this side negative max, okay? And the top and the bottom are going to be our 0 spots, okay? Firstly, let's just see if this setup makes any sense, okay? Let's say if our phasor is over here, okay, so it's pointing at positive max. Then, if we move this way, right, remember our phasors always go in the anti-clockwise direction, we're now going to move in this direction right here. So we're moving from positive max to negative max, okay? And so therefore, to move from positive max to negative max, we must go through 0 first, right? So that makes sense. That makes sense why this 0 is here. So we'll move, and then we will now be at the 0 point, okay? And then we'll go across again. And once we're at 0, if we keep going, okay, if we keep decreasing our value, we're going to get to negative max, okay? And so therefore now we're here. And so if we want to go to positive max again, we need to increase our value. And so if we increase our value back to 0, and then we further increase the value, we're going to be back at positive max, okay? So that is how the phasor diagram works, okay? So as we said before, the voltage across the resistor, so VR, leads the voltage across our capacitor by 90 degrees, like we see over here. So this is the voltage across our capacitor. And like I said previously, our current phasor is in phase with the voltage across our resistor. So we can draw it just on top like that, okay? So what does this mean? Remember when we have our circuit, so we can draw our AC circuit like here, and we have our resistor. This is our RC circuit. As we can see here, the voltage across the capacitor is max, and therefore the current is also at max, okay? Remembering back to our capacitors, when the current is max, that means that there is no charge buildup on the capacitor. Because when we have our circuit with just a capacitor, let's use a DC circuit this time to make it easier to remember, okay? When we initially turn on our power supply, the current is max because there is no charge buildup across our capacitor. And therefore, because there's no charge buildup across the capacitor, the voltage across our capacitor is going to be 0 volts. 0 volts, like so, okay? And so that is what we see here. When our current is max, we can see that the voltage across our capacitor is at a minimum. It is at its lowest value, 0, okay? And if we were to copy this phasor diagram, okay, and now let's move up by 90 degrees. So move in the anti-clockwise direction by 90 degrees. So therefore, our voltage across our capacitor is going to be over here, and our current is going to be in phase once more, okay? And the voltage across our capacitor is going to be at a positive max, okay? So in this scenario, we can see that our current and the voltage across our resistor is at 0. So it's at its lowest value, it's at a minimum. But the voltage across our capacitor is at a max. And so if we go back to our simple DC diagram, if the voltage across our capacitor is a max, that is when we have the max amount of charge on the capacitor plates, okay? So our voltage is now Vmax. And when our voltage is Vmax, this is when our voltage across our capacitor is equal to the voltage across our supply, okay? And so therefore, because we have two opposing EMFs, our current is 0. And what do you know? That is exactly what we see over here. When the voltage across the capacitor is at a max, our current is also 0. And so the final thing here is I'm going to give you a little memory tip, okay? So something to help you remember something in the exam. Not gonna lie, this didn't really help me in the exam, but my teacher taught it anyways, so it might help you. So I'm gonna show you here now. This is an acronym, and the acronym is ICE, okay? And so what this is basically saying is that the current in an RC circuit leads the EMF, okay? So leads the supply. So in an RC circuit, current leads the EMF, also known as the supply voltage, okay? And so what that looks like is our current right here leads the EMF, which is this point right here. And the C is to remind you that this is an RC circuit, okay? There is another acronym for LC circuits as well, which we go into later in the playlist, okay? And that will be it for this video. See ya.